We're going to be talking about individual gas laws today. We want to start off with one called Boyles Gas Law. Boyles Gas Law shows the relationship between pressure and volume. So Boyles Gas Law, this equation of the initial pressure times volume equals the final pressure times volume, only if the temperature stays constant. Now, if you're looking at this equation, it might look somewhat familiar to you. We've already talked about the combined gas law. So we know that's P1 V1 over T1 equals P2 V2 over T2. If we know that temperature is held constant, that means that these two values are the same. So even if they were something like, 300 Kelvin and 300 Kelvin, and they stayed the same, if you multiplied 300 over to the other side, they would end up being one on the denominator and one in the numerator, so they would cancel out. So that means whenever temp is constant, that means you can get rid of whatever variable is constant, and you're left with only what is going to change, which is P1 V1 equals P2 V2. And that's how Boyles Gas Law is actually figured out. So the cool thing is, as long as you know the combined gas law, you just take away one of the variables and you have one of these three laws we're going to learn about today. All right, well, let's cut to a demonstration that shows the relationship between pressure and volume. So take a look at that. For our Boyles Law demo, we're actually going to use a regular old potato. What I'm going to do is I'm going to take a knife, I'm going to cut a slice of the potato and another slice of the potato. I'm going to discard the leftover pieces and the knife. I don't need that anymore. But what I have here is an empty tube, and you can see through it that it's hollow. And I have what's going to be called a ramrod. What I'm going to do is first shove a piece of the potato into one end of this tube. All right, so to do that, I'm just going to push down really hard. There we go. You can see that I put the piece of potato into that end. All right, that's plugged up. Now I'm gonna do it on the other side. Shove a piece of potato in there. A little messy, but okay, I'm gonna shove it in. Now you can see that this is no longer hollowed out. There is a piece of potato on each end. Let's think about that, what's happening. So the potato pieces are plugging up this tube. Inside there is gas, right? So we know there is a certain volume of gas and there's a certain pressure inside of here, probably close to atmospheric pressure. What's gonna happen if I push this potato in further? Now that the potato plugs are pushed closer together, there's going to be a smaller volume. We squeezed it. But because we decreased the volume and squeezed it to a smaller space, what's gonna happen to the pressure? It's going to build up, right? Because of Boyles Law, we see the relationship we call an inverse relationship. As the volume decreases, pressure is going to increase. And we can prove that by just simply taking the ramrod and shoving one end of the potato towards the other, and we should see the end of the potato come out. So let's see if that really happens. All right, so here we go. 1, 2, 3. Whoa! And there it went. It shot all the way out and actually shot across my room and hit my wall, which is pretty awesome. But what you just saw was as the volume decreased and I shoved it so that the volume went even smaller, the volume went down, the pressure dramatically went up, caused that high amount of pressure, and eventually, whoop, shot the potato out. So that's an example of Boyles Law because of the inverse relationship between pressure and volume. Now that you've seen the Boyles Law demonstration, let's make sure we break it down to understand it. This is a chunk of potato and this is a chunk of potato inside of that tube. What we want to look at is that we understand that between these two chunks of potato was a certain volume, right? Also, inside between those chunks of potatoes, there was a certain pressure. But now we know that when we push the one potato closer to the other side, so say we move that chunk like here, we now know that there's a new volume, right? So that's a new volume and a new pressure. So the question is, what is the relationship between volume and pressure? Well, I think that we explained it well and showed in this demo that as we made the volume go down, right, by pushing that piece of potato over, you were squishing the gas, making the volume smaller. And by doing so, you actually increased the pressure. So by doing that, increasing the pressure and lowering the volume, you show that there was an indirect relationship. And that's exactly what Boyles' law shows. It shows that indirect relationship. The next gas law we'd like to talk about is called Boyles Gas Law. Boyles Gas Law shows the relationship between volume and temperature. And since pressure is being held constant, we know that pressure will no longer be in the combined gas law equation. So the question is, what is the relationship between volume and temperature? As one goes up, does the other one go up? Or as one go down, does the other one go down? We know from Boyles' law that as volume went down, pressure went up. So they had an indirect or inverse relationship. What's the case with Boyles Gas Law? Well, let's think about this realistically. Charles actually was a balloonist, so he was interested in hot air balloons. Think about how a hot air balloon actually works. With a hot air balloon, if you increase the temperature by heating it up, what you do is also increase the volume. Why? Because if you spread out the gas, it has more energy when it heats up. It's also going to spread out and be less dense, which means it's going to be lighter than air. So from what we see, we know that Boyles Gas Law shows that there's a direct relationship between volume and temperature. Well, let's watch the demo first, and then we can come back and really break this down to be sure. Okay, science fam, to demonstrate the relationship between volume and temperature of a gas, I've got an Erlenmeyer flask here. I've got a hot plate right here, heated up, and I've got a balloon. Now this flask is empty. So what I'm going to do is I'm going to take the balloon and put it around the flask, okay? But we know that it's empty, but is it really? No, there's gas inside of here, right? There's air, atmosphere. So what I'm going to do is I'm just simply going to put it on this hot plate. All right, and as I put it on the hot plate, this hot plate is going to heat up the air inside the Erlenmeyer flask. And as you can see, and I'll move to the side so you can watch that better, as the air inside heats up, the temperature goes up, and so does the volume of the gas. And you can see that the balloon is already moving. And there you go. Look at that. So at first it looked like there was nothing in it, but as it heated up, we saw that the volume of the gas expanded once the temperature went up. Now that's a direct relationship, and that's what Boyles' law talks about. As the temperature of a gas goes up, so does its volume. Now, if we shut this off and let this cool down, eventually the temperature would go down and so would the volume, and this balloon would deflate again. But this is a direct relationship explaining what Boyles' law is really talking about as a gas law. Now that we just saw that Boyles' law demo, let's make sure we understand what's going on. So originally in that flask, there was just a certain volume, right, of gas. And there was also a certain temperature. But we know that as we heated up that Erlenmeyer flask, what happened? The temperature increased. And when the temperature increased, what happened to the volume of the gas? It increased as well. And that's what allowed for, right, the actual balloon to expand. So by doing so, we know that we increase the volume with the increase in temperature. So what does that mean? That means that that is a direct relationship. That as temperature goes up, so does the volume of a gas. And vice versa. As temperature cools, so does the volume. You maybe have seen that before if you've ever purchased a balloon for someone's birthday party in the winter. The balloon is full when it's inside the store, but when you bring it outside to your car and it's cold weather, the balloon kind of shrivels and gets a little bit sad, right? There's not as much volume. But once you bring it back in the house and it warms up again, you notice that the balloon perks up again. And that is Boyles' law in action, just showing you that as temperature increases, so does volume of a gas and vice versa. That's called a direct relationship. The final gas law we're going to talk about is Gayluss Gas Law, which shows the relationship between pressure and temperature. Notice that in this equation, volume is held constant, so volume is not part of that combined gas law equation. Now, Gayluss Gas Law talks about, hey, if temperature goes up, what happens to pressure? Well, let's think about that in like the tire pressure inside a car tire. Well, if the temperature goes up and gets hotter and hotter, that means those gases are going to get more and more energy. If they have more and more energy, they're going to push on the tire even more. So I think it's safe to say that as temperature goes up, we're going to expect pressure to go up. And vice versa. If the temperature goes down, it gets cooler, the gas gets less energy, so it pushes on the walls less. So that pressure should go down. We'd call that a direct relationship. But let's watch this demo to really make sure that that's the case. For our Gayluss X demo, we're going to take an empty soda can. What we're going to do is I put just a little bit of water in there so I know it's heated up. I'm going to heat it over the Bunsen burner until it's nice and hot. And then, since there's only one opening in the can, going to invert it and put it upside down into this cold ice water. Now what's going to happen is it's going to go from extremely hot to extremely cold at a very quick pace. What is that and how is that going to affect the pressure? Let's find out. So now I have the can, let's start heating it up. So I'm going to put it over the Bunsen burner flame, and you can hear it sizzling actually already. So this is getting the air, the temperature of the gas inside the can super hot. And we know that because this is open, the gas inside is still going to be at atmospheric pressure. But once I take this hot can and put it upside down into this cold ice water, the temperature is going to dramatically drop. And what's going to happen to the pressure? Let's find out. All right, so we got a nice hot can. Let's put it, invert it in there. Whoa! You heard it sizzle, but what you might not have seen is that the can actually crushed. The question is why? Why did the can crush? Well, let's think about this. Hot temperature, cold temperature. So temperature dramatically decreased. The pressure inside was regular. What happens to pressure when the temperature dramatically drops? Drop in temperature, drop in pressure. So if inside this can, the gas got really cold, the pressure dramatically dropped inside, and there was nothing holding the aluminum can open. There was nothing like atmospheric pressure pushing it open. So what happens? The gas and air around us right now, the atmospheric pressure actually crushes it. So since the air pressure inside of the can was so low, regular atmospheric pressure crushed it. And there you have it. Just by simply putting the hot can upside down, dropping the temperature, we dropped the pressure and it crushed. So this is explaining the direct relationship between pressure and temperature. As temperature goes down, so does pressure, and we saw that. That is what Gayluss Gas Law is exploiting. By using that direct relationship, we can have a simple equation to solve problems and estimate what happens with the gas. So let's recap on that demonstration that showed Gayluss Gas Law. Basically, we had a really high temperature to start, didn't we? And because of that high temperature, right, the gas was really hot inside. And we had a starting pressure. No big deal. But when we took that hot can, inverted it, and put it into the cold ice water, what really happened? Well, the temperature dramatically dropped, and the pressure of the gas inside the can also dramatically dropped. Since that happened and the pressure inside the can became very low, outside atmospheric pressure, which remember is always pushing on us, not to mention the pressure from the water once it was submerged in there, that all pushes on that can and ended up crushing the can. So what it demonstrated and showed you is that, yes, as temperature decreases, so does pressure. We call that a direct relationship. That as temperature increases, so does the pressure, and vice versa, a direct relationship. So now that you've looked at all three gas laws, we know that they all have equations that basically steal from the overall combined gas law equation. Remember that as long as you can say one is constant. So, for example, Gayluss Gas Law says that volume is held constant. We can cancel out the volumes and be left with P over T equals P over T. We can use those general formulas and equations in order to help us predict that, hey, if I did drop the temperature of this gas by this much, what would the new pressure be? So it allows us to estimate and predict what the changes are. But understanding whether it's an inverse or direct relationship will be important. And that's what we're going to continue to work on as we work on the math as well. So nice job listening, Science Fam. Hopefully you have a better idea of the 3 gas laws, which include Boyles Law, Charles Law, and Gayluss Gas Law. And hopefully you see the relationship of them to the combined gas law. Take care.